We are live now, so welcome everybody to today's seminar. We have a pleasure to have a distinguished seminar speaker today, Dr. Khaled Letaief from HKUST Hong Kong, and he will be giving a talk about his vision and actually unfolding vision, I guess now globally, of the 6G and where is it going to lead us. I'm Zbigniew Wasilewski from EC department and associate chair for research, and I have the pleasure to just make this brief introduction. However, I will pass on to Chairman Shen, who knows Dr. Letaief personally very well, and I think he will be much better suited to make the full introduction. Okay, so thank you very much, and Chairman, I turn the floor to you.
Yeah, thank you, Zbigniew. Good morning, everyone. My name is Chairman Shen. I'm a professor in the Department of Electrical and Computer Engineering. I would like to welcome you to this ECE distinguished lecture entitled 6G, the next AI-empowered and hyper-connected world, to be delivered by Dr. Khaled Letaief, Fulbright Professor of Engineering and the Chair Professor at Hong Kong University of Science and Technology. It is my great pleasure to introduce Dr. Letaief, who has an outstanding career. I have known Dr. Letaief for more than 25 years, not only as an international, well-recognized researcher in the same field, but also a close friend. Dr. Letaief received his bachelor, master, and a PhD from Purdue University in the US. He is a member of the United States National Academy of Engineering, fellow of IEEE, fellow of the Hong Kong Institution of Engineers, and a member of the Hong Kong Academy of Engineering Sciences. Dr. Letaief is also the founding editor-in-chief of the prestigious IEEE Transactions on Wireless Communications. He is the recipient of many distinguished awards, including the 2021 IEEE Communications Society Best Survey Paper Award, 2019 Distinguished Research Excellence Award by Hong Kong UST School of Engineering, 2019 IEEE Communications Society and the Information Theory Society Joint Paper Award, 2016 IEEE Marconi Prize Award in Wireless Communications. Dr. Letaief is well recognized for his dedicated service to professional societies, and in particular, IEEE communications, where he has served in many leadership positions. These include the IEEE Communications Society President, the world's leading organization for communications professionals with headquarters in New York City, and members in 162 countries. Since 1993, he has been with Hong Kong University of Science and Technology, where he has held many administrative positions, including Dean of Engineering, the head of Electronic and the Computer Engineering Department. He is currently serving as member of the IEEE Board of Directors. Just a note, this lecture is going to be recorded. During the lecture, please use the chat function to write down your questions. We will have a Q&A period at the end. Thank you. Without further ado, Khaled, please, the floor is yours.
Well, thank you so much, Sherman, I'm extremely pleased to be here. I wish I was there personally, physically. I'd like to thank the university, your department, for your kind invitation. And I would like to thank everyone for attending my talk. So this is the outline of today's talk. I will briefly start with kind of an introduction to 6G. Why do we need 6G? Somebody can say we're very happy with 5G. And I'm going to try to describe in a brief way the roadmap to 6G. And then I'm going to try to argue that 6G AI is going to play a very, very important role in 6G. So I'm going to try to explain the reasons as well as the challenges and what type of solutions we're going to provide. So we're going to talk briefly about intelligent edge AI. And I'm also going to be putting a little bit of emphasis on what I call AI-based optimization, which is going to be very critical for resource management and optimization of wireless network. I guess I just want to have one slide for those of you who are not familiar with HKUST. HKUST is in Hong Kong, obviously. It's the Hong Kong University of Science and Technology. It's only 30 years old. It's only 30 years old. But it is considered to be a good university. In fact, by 2020, it was ranked the #1 world's top times of higher education young university. I don't know whether we are still young or not, but at least we are up there. And in 2020, in fact, according to the QS World University ranking, the School of Engineering was ranked number 18 in the world. One of the reasons I accepted to give this talk is because I really have a lot of respect for the University of Waterloo, and I also have a lot of respect for the faculty there and the students. And UST and the University of Waterloo has a lot of common features. They are both one of the top engineering schools in the world. And when I was the dean of the School of Engineering at the HKUST, and when I was the dean, I worked very hard to establish a very close relationship between the university, your school, the School of Engineering, as well as at Waterloo, as well as UST. And we now have what we call a dual degree between HKUST and your university, where students can, for example, PhD students can end up having 2 degrees, a degree from a PhD from Hong Kong UST and a PhD from the University of Waterloo. I think this is the best of both worlds, and I hope that students will take advantage of that. But then there is another thing. We have a very common thread between the University of Waterloo as well as UST, particularly between this in the department. And I think one thing that I feel very proud of is that both departments, the Department of Electrical ECE at Waterloo, as well as our department, both were able to have 2 presidents, a sitting president, chairman of the IEEE Communications Society, and I was also the president of the IEEE Communications Society. So both universities share this honor of having the pleasure of having a president of one of the major IEEE societies. So let me go back now, trying to basically talk about wireless communication. I guess there is no doubt whatsoever that wireless communication is an extremely important technology. And I found it interesting to know that in 1926, I think most of us know who is Tesla, who was most famous for designing AC electricity. And what he said is kind of interesting. In 1926, he said, when wireless is perfectly applied, then the whole earth will be converted into a huge brain. I don't know what he means by a huge brain, but what he predicted in 1926 is that we're going to be able to communicate with one another instantly, irrespective of distance, and we're going to be able to see each other and talk to each other as if we are in front of each other, irrespective of how many thousands of miles. So I found that this is an incredible prediction in 1926. So the question, are we there? Are we there? And then I think it's worthwhile to look at the wireless evolution, and you will see that wireless has gone through different generations. Every 10 years or so, we have a generation. So in 1990, we started with the second generation, which was mainly targeted towards people to people. Then we went into 3G, 4G, and nowadays we are going through an exciting phase of introducing 5G, which is happening, which is now available in about 70 countries around the world. And there is no question that there is a huge economic impact due to 5G and associated wireless communication. But I think the excitement about 5G and what 5G is going to do for us, in my mind, is going to be dwarfed by what is going to happen in the next 10 years with the arrival of 6G, which is expected to happen around 2030, where it's going to be a paradigm shift moving from what we call connected things in 5G to connected intelligence, where we're going to expect a host of new services such as digital twins, industry 4.0, holographic communications, telemedicine, and a host of services that's going to really make our life extremely exciting. But then when you actually look at it, a lot of talk about 5G, and I think a logical question, why do we want to go to 6G? Why can't we just basically survive with 5G? Isn't it good enough? I mean, there is a lot of hype about that. And I guess the easy answer is that wireless is very, very special. And wireless communication is different from other technologies in the sense that every new generations would require significant innovation. And in particular, wireless has been growing at an exponential rate. And as I mentioned, 5G has been introduced around 2020, but as you can see, this is an estimation from ITU, the International Telecommunication Union, which is a United Nations. Basically, they predict that the growth of wireless is going to continue at an incredible rate. In fact, it's going to grow at an incredible annual rate of about 54% per year in the next 10 years. Think about what technology is going to continue to grow at 54%. And in fact, the global mobile traffic is estimated to reach over 60 trillion gigabytes per year in 2030. What this means is that the current 5G system will not be able to support this tremendous increase in the system capacity, as well as the services that I have just mentioned. So with that in mind, we need 6G because we will not be able to support what I've just said, but also the extreme requirement, such as the delivery of very high reliability, extremely low latency, and so forth. But one thing that is extremely important is that the expectation as we move towards 6G is going to be a convergence of communications, sensing, control, and computing. And this is extremely important, and 5G is not going to be able to do so. So therefore, there will be a move towards 6G, and now there is a huge number of activities around the world, in Canada, in the US, in Finland, in Korea, in China, in Hong Kong, in Japan. People are looking into 6G, and 6G is going to be a paradigm shift. It's going to be having extreme, what I call extreme requirement, such as, for example, data rate moving all the way to 1 terabit per second. This is incredible. We're going to have a huge energy efficiency, very, very low latency. And what is really amazing is that now we're going to be extending the frequency range, going all the way to the terahertz. This is going to open up a huge opportunities to bring sensing and joint sensing and communication and so on. At the same time, it's going to involve what we call a 3D type of networking, where we're going to see now the integrations of satellite communication, cellular mobile communications, as well as maritime communication together in one system, in order to provide a global, ubiquitous, always-on broadband communication. And more importantly, it's gonna basically require what I call connected intelligence, where we're gonna have an AI networking hierarchy with machine learning capabilities. So when we actually look at the difference, so what we see here, kind of this can of red place actually shows what is 5G versus what 6G is going to be. And what we can see that the difference is going to be huge. For example, in terms of latency, we're talking about going to 0.1 millisecond end-to-end latency. We're talking about spectral efficiency going to 100 bit per second per hertz. This is a huge, as well as the massive connection going to 100 million devices per square kilometer. So these are extreme requirements, and which it means that we need to have breakthrough, scientific breakthrough, in order to make sure that 6G is going to deliver all of these requirements. So where do we stand now? So where do we stand is that this is typically what we talk about when we talk about 5G. So 5G is described typically by this triangle where we're going to be talking about three specific services. The first one is this massive machine kind of communication. This one is basically trying to deliver very high data rate. And the other key service will be trying to deliver ultra reliable and ultra low latency communication. And this is in order to meet the requirement of different applications. But what we're going to see is that now we're going to move in an initial stage to what we call 5.5G, where we're going to have now, as you can see, a new kind of services they're going to be included. And this is what we call Huawei vision. We call it 5.5G, where we see we're introducing a new kind of quality of service, what we call, for example, UCBC or RTBC, which stands for uplink-centric broadband communications or real-time broadband communication. But eventually we're going to move to 6G, and what you will see here, and I think this is a kind of I won't go through each one of them, but the point I'm trying to say is that the requirement and the type of quality of service, the type of things that 6G is going to deliver is going to be much, much more than 5G. And the reason is that we're going to have to deal with different applications. For instance, we're going to have to deal with holographic communication. We need to do immersive, the cloud. We're going to do digital twins. We're going to be doing things like Industry 4.0, autonomous driving. And all of these would require much, much more extreme requirement, and therefore much more kind of quality of service, more than the three required by 5G. So in this context, 6G is going to be special. 6G is going to represent a paradigm shift from 5G towards what I call AI-empowered network. And this is going to be the key differentiator. So we're going to be looking into an AI native intelligent radio, and we're going to be trying to have a system where we're going to be seeing AI and machine learning, neural networks everywhere. For example, that could be an AI native transmitter, an AI native receiver. We're going to see resource management based on AI and machine learning. And this is going to go even towards the networks or towards the devices, where we're going to see the integration of software and hardware. So really, for those of us working in wireless communication, the future is extremely bright. The future is extremely exciting, because it's going to move us to kind of a new design philosophy. This is going to be transformative, and it's going to allow us to have a lot of opportunity to make impactful contribution. So as I said, AI is going to be playing a very, very important roles. And I think it's very interesting to argue, what is really AI? Why are we talking about AI? And everybody's talking about it now, but then the question is this really something new? And the answer is no. AI has been here since 1950, from when Turing actually published his major work on basically whether machines can think or not. But really what was incredible is in 1956, there were a group of mathematicians, they had a workshop and on AI. That was the first workshop on AI. And we will see in this picture, for example, famous scientists particularly Claude Shannon here. This is kind of the scientist that came up with the first workshop on AI. But then in terms of practice, in 1957, from Cornell, we have the first, what we call the first artificial neural network that was implemented in practice. And since then, obviously, AI became an extremely popular field, and significant amount of funding has been pumped into AI in the 60s and 80s. But then what they have predicted in terms of how good is AI, nothing happened. And consequently, in the 1970s to the 1990s, we had what we call the AI winter, where basically people gave up on AI. However, and around 2015, particularly with the when the AlphaGo, basically developed by Google, DeepMind, was able to defeat a professional Go player in 2015, and this has changed the whole picture, and AI now is back on the map. And in fact, one of the reasons is also it's back on the map because the two secrets behind AI success is basically the computing power as well as the big data. However, there are a lot of challenges with respect to AI. And I think I want to mention, obviously, AI is going to involve a model that we need to train. And typically, in most of the application we're going to be looking at, the model size can be huge. Also, the speed, for example, when you connect AI with communications, how are you going to train the network and so on, is also going to be a serious problem. The energy associated with using AI could be huge because it can end up draining a significant amount of power. And finally, when we start talking about AI, we're talking about using, for instance, your own data, and privacy security becomes a big issue. So to deal with these challenges, a lot of people have been trying to figure out how to do that. And one possible solution in order to pave what we call for the last mile is what we call edge AI. In other words, trying to use intelligence or AI at the network edge in the context of wireless communication. In other words, try to be closer to the users and try to then minimize the impact on the network backbone, try to minimize the energy, try to minimize the latency, and so on. So recently, there has been a significant amount of interest in terms of applying AI at the edge, where we're going to do the data collection, the data processing, the transmission, as well as the consumption at the network edge. And how are we going to do that? Well, there are different ways of how we're going to do that. Well, the first one is what we call a consensus model aggregation. This is kind of a decentralized learning where we're going to try to learn a global model, because basically the basic principle in AI is trying to train a model. But the way we're going to do that, in order to try to do that efficiently, we're going to try to do that in a decentralized way through peer-to-peer communications. The second option is trying to do what we call a model splitting learning, where we're going to try to allow collaboration across edge devices and edge servers by trying to partitioning the model parameters so that you don't need to try to estimate a lot of parameters across the edge nodes. And the last one, which I would like to speak a little bit about, is what we call the federated learning, where we try to train a global statistical model without accessing the edge devices, and therefore you're going to preserve the quality, the data and privacy of the user. So specifically, think about now AI, and you're going to have actually the internet and so on. And what you're going to try to do is that you're going to try to get the data from users in order to train a global model. And when you do so, obviously you're going to run into trouble, because obviously there are rules. For example, in Europe, you cannot get private data. And if you're going to train a model, you're going to have to get the data, and that's going to pose a problem. So federated learning is now an extremely hot topic, where basically we try to train a model. However, the way we're going to do that, we're going to try to train the model at different devices, using their own local data, but then instead of sending their private data, they only send some what we call the weights of the model, not their private data. And by doing so, then at the server, you're going to be able to use those weights in order to update the global model without having access to the original data of the user. And this will preserve privacy. Now, this is a very, very hot area, as I said. But one of the problems here is that when you're going to try to use federated learning, you're going to have a lot of devices everywhere. And therefore, you need to update the model at the local mobiles as well as at the server. And by doing so, you're going to have a lot of rounds of communication between the mobiles and the server. And that's actually going to require perhaps thousands of rounds of communication, which is going to slow the system, is going to actually burden the backbone, and it's going to create a lot of problems. At the same time is that when within one round of communication, think about the model is going to be huge, and the overhead is proportional to the model size, and that's going to make perhaps federated learning a bit of a problem. And the other problems include how heterogeneous the data. So typically, from a statistical perspective, we talk about IID versus non-IID data, which I'm going to explain a little bit about that. So in order to deal with this problem, instead of actually dealing with the original federated learning, where you're going to have a server at the cloud, where you're going to try to have access to all the nodes, which could be cars, which could be mobiles, could be IoT devices, that's going to create a lot of problems. So in order to solve these problems of the communication round and so on, people actually propose what we call edge-based federated learning, where we basically, an edge server, that means at the base station, closer to the base station, basically is going to try to do federated learning just for users for that particular base station. So obviously it's going to make it better because the edge is going to be closer to the users, but it's going to have few clients, but maybe it's going to solve a lot of these problems. So one of the results we did, we tried to compare the traditional cloud-based federated learning as well as the edge-based federated learning. And what we will see, obviously, is that you lose in terms of performance when we try to do edge-based federated learning. So the question said is, can you do it better? Can you do something better? And what we actually did, this is an area that we propose, is to use what we call hierarchical quantized federated learning, which aims at reducing the communication latency and the overhead in the training process by introducing edge servers in the middle between the cloud as well as the users, all right? This will allow many low communication cost aggregations between the edge server and the users, and then infrequent aggregation between the edge server as well as the cloud. And at the same time, in order to minimize the overhead for a given round, we also introduced quantization in the weights and so on and so forth. So how does it work? Well, basically, instead of doing a cloud base or an edge base, we're actually introduced this idea of edge servers as mediators. So specifically now we're going to have edge servers everywhere, and they're going to be multiple, obviously, base stations. So they're going to be multiple edge servers. And now we're going to have access to maybe L edge servers, and each of them, they're going to actually do multiple aggregation in order to train the model. And then after doing multiple aggregation, then there will be aggregation between the edge servers as well as the cloud. And by doing so, what we have found is that this scheme will actually be better than the cloud-based federated learning, and therefore we've solved this particular problem, all right? So one of the things that is missing in many of the papers on federated learning is the idea of trying to analyze the system. And it turns out analyzing machine learning is extremely difficult. And we try to do so by trying to pose this as a mathematical problems. So in this context, what we would like to do, I guess, you're trying to do an aggregation, you're trying to minimize a loss function in federated learning, whatever that particular loss function for a particular client or a mobile user, and you need to make some assumptions. For example, things like the gradients, because you're going to do a stochastic gradient in order to achieve a certain accuracy and converge for the weights. And there is some condition, we call it L-Lipschitz condition, which is kind of important in order to guarantee the convergence of the gradient descent method. So somehow you basically look at the function you want to minimize, and you want to make sure that the norms of the gradient basically follows this condition. And if you can do so, then potentially you may end up with an analysis. But then even if you can do that, and we did this, so for example, we end up with a theorem like this. What we did, basically, we're trying to do, remember we were saying we're going to do an aggregation between the client and the edge, and we're going to do that tau 1 times, and we're going to do an aggregation between the edge and the cloud, and we're going to do that tau 2 times, and we're going to quantize these rounds between the clients and the edge, and the edge and the cloud. So what we did, we end up with kind of an upper bound that actually looks pretty complicated, but actually it's extremely useful, because one of the things that is useful, for example, is tell us how are we going to associate the clients with the servers. And basically this GURS, if you have time to look at it, I guess in detail later on, it actually says a lot of things. For example, it tells us that the edge and client association has no influence whatsoever on the convergence of federated learning. And we've actually tried that. We tried that, and what we have seen is that we tried this on a data set with 50 clients, and we have 2 edge servers, and we actually try to have different association. For example, you have 25 users per client, or you have only 5 users per edge and another 45 with the second edge. And what we will see, there is no difference whatsoever. The convergence and the accuracy is exactly the same, which actually means 2 things: that if you want to accelerate the training process, we only need to minimize the communication round by simply minimizing the communication delay of the slowest client. So let me move forward here very briefly. I guess I want to introduce something pretty interesting, namely, one of the problems with federated learning is that you would like actually to get the weights from different users. And one of the things you need to do is basically you want to do compute the weights of the models from each set of users, and we're going to do weight averaging. So the problem is that for the weight averaging to work, you would like to have homogeneous model structures. You want them to be the same. And the problem is that this is not possible, because typically you're going to have heterogeneous users, and therefore, because you may have mobile devices, IoT devices, and therefore the weight average is going to suffer from what I call structural misalignment with regard to the unmatched parameters. So this is actually a serious problems in federated learning. And what it really means is that federated learning would not work well under the ideal condition where you assume that you have IID distribution. So one thing that we have started working on is something pretty exciting we call knowledge distillation. This is kind of an alternative method of model aggregation, which will be applicable to heterogeneous model architectures. So specifically, the idea of the knowledge distillation is like transfer learning, where you actually try to train the model on what we call a teacher, a teacher model, which is actually a very large model. But then you try to basically transfer that knowledge from the large model into a smaller model that you can use, for example, on the mobile devices. So in a sense, a small model is trained to mimic a pre-trained large model. So this is a pretty interesting area where you simply introduce what we call the notion of logits of the data sample, where you introduce, in a sense, a distillation loss, which try to minimize the difference between the parameters you estimate from the teacher model as well as the student's model. So by doing so, you will be able to converge and be able to run the system on a smaller like nodes and IoT devices in comparison to the bigger one at the cloud. So what we did recently, we had a paper where we basically trying to look into how we can do distillation. So what we have found is that the problem with the conventional federated learning, which is extremely hot now, is that it cannot deal with heterogeneous kind of models. But what we have found is that when you do knowledge distillation, it actually gonna work out, and it worked out pretty well. So specifically, we found out that federated distillation is very flexible. It provides not only orders of magnitude reduction of communication overhead compared to traditional federated learning, but also, and this is the most important thing I would like you to remember, is that it deals with a very, very important challenge in federated learning, namely the idea of heterogeneous model. So this is a paper we just basically presented in ICC in Korea last week, which actually talk about this particular model. So now let me actually conclude with the last part, and this is actually perhaps the most interesting component, is trying to deal with how do we deal with the optimization, resource allocation, resource management of wireless network. And what we're gonna see is that now the system are gonna be so complicated. You're gonna do cloud radio area network. We're gonna have machine learning. It's just going to be so complicated that typically we're going to run into trouble. So specifically when we deal with wireless network, we typically, whether you are in control or whether you are in wireless, you're going to have to deal with minimizing a function subject to some type of constraint. And typically these constraints could be integer, could be non-integers. For example, you want to minimize the power, but then you have to have a resources, subject to a certain transmit power and so on and so forth. And what happens typically is that you're going to have not only continuous parameters, but also you have discrete parameters. And this typically make it the mixed integer, nonlinear programming problems, which are typically NP hard. And this is typically what happened in wireless communication system. So how do we deal with this challenge? Well, typically, and the best way to deal with is to deal with what we call a mathematical optimization. When we do mathematical optimization, it's beautiful because it relies on a well-defined model, and we can optimize it, we can find efficient solution, everybody is happy. But then now people are interested to see, can we use machine learning? It's gonna be data-driven, but more importantly, it can, in a sense, deal perhaps with very complicated system that mathematics would not be able to deal with. And so the question is that, is it possible that I use machine learning, but then at the same time, I would like to make sure that the machine learning is going to be able to be scalable. In other words, deal with thousands of base stations. Can it be real time that I can actually have the model converge in real time? Can I do it in a distributed way? Can I do it automatically? These are a lot of big questions if you want to use machine learning in wireless communication. So let's actually take a break. What we would like to do, can we use machine learning to optimize the system, to do resource management and so on and so forth? And a lot of people actually now are very, very interested in this problem. And typically, but then there is an issue. Typically, when you try to use an optimization algorithm, if you would like to basically replace it by a neural network, then most of the time, actually, you're going to have kind of what we call a black box. In the sense, it just works and you have no idea how it works. But then the problem is that it's going to need a very large model. It's going to need a lot of samples in order to the model to converge. And somehow it's very difficult to handle constraint. So recently, there were a lot of interest to come up with a new approach, which we call an optimization policy learning approach, where the idea is that you want to use machine learning by learning the optimal policy in a specific problem. For example, a lot of the mixed integer nonlinear programming problem can be solved through what we call a tree search. We call it, for example, the branch and bound, which will allow you to solve this NP hard problem through a tree search. And so the idea is that if the machine learning algorithm learns how the branch and bound algorithm works, I can mimic that, and accordingly, I will be able to estimate and do the optimization and perhaps potentially even solve NP hard problem. So this leads to what we call the learn to optimize. So this is a new technique, and we have a paper that was published in 2020 to introduce this approach. And what we have found is that this technique can somehow give you near optimal solution at affordable time. And the idea is that you want to learn how the traditional algorithm like the branch and bound works, and you try to use machine learning to mimic that behavior we call imitation learning, and end up with good solutions. So this is a new design paradigm for large-scale optimization. So we've done a paper in 2020, but then there were also in 2018 and many other areas, especially in statistics and so on, they started to use this idea of learn to optimize, where you basically, it doesn't matter. I don't need to have a mathematical model. For example, I want to do an optimization. I can have the input to be the channel states. And then I have, instead of an optimization algorithm, I simply replace it by a neural network and try to figure out the output. So this paper, for example, was one of the original papers that tried to do this and tried to come up with the sum rate maximization of interference channel, which is, by the way, an NP hard. And we know, for example, that the WMMSC can give you a good performance obviously for a small scale system. And what they have found is that they prove in this particular paper that this learn to optimize using deep neural networks can actually give you good performance. This is great. So we actually look at this and we say, okay, let's try to look at this and let's actually try to reproduce those results. And what we have found is that here we're looking into a system where in an interference channel, and what we have found is that this approach, which is based on the use of deep neural network, is that when the number of users, and this is very important, when the number of users is small, in fact, you achieve almost the perfect, it's almost the perfect performance. On the other hand, when the number of users increase, notice that the performance of the DNN-based AI is not as good. It actually goes pretty bad. So basically, the scalability doesn't work. And this is a huge problem because we're talking about massive machine communication. More importantly, when we do this, what we call based on MLP and DNN, we're going to need millions of samples to train the network. And that's going to pose a problem because it's not going to be real time. So that led us to a question, which is a very important question. I want to use AI, but what type of structure should I use? Is really the MLP based on the DNN is a good structure. And it turns out it's not a good structure because it does not exploit the information structure in the data. On the other hand, there was a very successful story, namely a convolutional neural networks for image processing has been very successful in image processing because it exploits the shift invariance and the local connectivity in images. So can we do that? Can we actually try to use something like CNN in this context? And this is actually that led us to something called the graph neural networks. So I think most of us are familiar with CNN, but then there is something else that is kind of an extension of CNN we call the graph neural network. And the graph neural networks can have application in recommendations, for example, in Netflix and so on, in chemistry, in point clouds, or even graph problems. So what is a graph neural network? These are simply a class of deep learning methods designed to perform inference on data described by graphs. This is as simple as that, but they are pretty neat. And more importantly, they can represent wireless networks, they can represent molecules, social network. But what we are interested on is that they can represent wireless network. So what do I mean? Why is this so? Because when I look at graphs, many real world systems, they basically have a graph structures. For example, social networks, wireless network, molecules, knowledge graphs. And in this context, and I want to compare it to the CNN, basically CNN, they try to do convolutions on pixels, all right? On the other hand, GNN, they're going to do exactly the same thing, but they're going to do convolution on neighbor nodes. And the trick here is that that wireless network can be put in the context of the graph, and therefore now you use the graph neural network to optimize the network. So specifically, wireless networks can be naturally considered as a graph, and this is pretty exciting. For example, we're talking about the cloud radio area network. We're talking about device-to-device networks, cellular networks, cell-free massive networks. For example, hybrid pre-coding in massive MoMo can be put in the form of a wireless a graph. A localization can also be put in the context of a graph. If you want to do channel estimation, even for massive MoMo, the channel estimation problem can also be put forward as a graph, and you can even put channel estimation as well as channel data detection together. You can represent it as a graph, and then you use the graph neural network to optimize the system performance. So let me try to just a couple of slides to give you an idea about something very important in graph neural network, which I call message passing. So in a graph neural network, you basically have multiple nodes. They could be connected, not connected, and typically you have a target node for whatever reason you want to do something there. Well, the idea of a graph neural network is that we take an input, a graph with a particular node, and we will also have edges, features, and basically try to compute a function that depends both on the features and the graph structure. And the key thing in GNN is what we call the message passing, which is key because somehow it operates by propagating the features on the graph by exchanging information between adjacent nodes like C and B or C and F. So the way it works is that typically it works into two stages. The first stage is somehow you want to encode the messages that exist in the nodes, and then you aggregate basically the information from adjacent node and then do some transform and somehow update the graph in another layer. So that's basically the key thing: message encoding and message aggregation. So how does it work basically? So the key idea is that when you actually have a node, you simply have different nodes, and you want to have to go to a target node at a particular layer, then there will be messages. And what you need to do is basically you would like to the network somehow to prepare these messages and encode them within a certain way, certain function. For example, in this case, this could be the message from a particular node U to a particular V at a particular layer, and then somehow this will involve a set of learning weights, and you actually encode that using this particular function, whatever it is, and basically pass it through an aggregation process to that particular node. Then the next stage is basically, as I said, will be the aggregation. So you encode it, then you aggregate it, and the aggregation is going to be based on what we call a pooling function, such as the sum or the maximum, and you do that. So that's basically how GNN works, and it's something, I'm not saying trivial, but it's something that we can learn. But what's really the key things here is that when you try to optimize, use GNN, you're trying to do an optimization, there is a very special algorithm, which we call a distributed message passing algorithm. And this is the classical algorithm to optimize an optimization algorithm on graphs. You want to use DMP in order to basically do an efficient analysis and optimize graphs. So if we would like to use GNN, we need to be able to use DMP. So one of the recent results we have, this is a paper we submitted to the Transaction on Wireless Communication. This is really a very theoretical paper we feel very, very proud of, is that we come up with a general way of how we can do wireless network optimization. And the idea is basically, it doesn't matter, take any optimization problem. You want to minimize the power, you want to maximize the rate, whatever it is. So obviously you want to minimize a function subject to some constraint. So the optimization variable could be, for example, a beamforming matrix. The objective function could be possibly non-convex. The constraint could be the channel state information. But what we have found and proving that for any graph, as long as you put the optimization in the form of a graph, then I can guarantee you that you're going to be able to find a DMP algorithm which will solve it. And that will actually make a big difference, because once you have the DMP algorithm, you're going to have a solution in a very efficient way. So let me give you some example how we're going to do that. So the proposal is to model wireless network as a graph and use graph neural network for resource management and optimization. And what we will show you that this can actually make the system scalable. And we're going to prove to you that we're going to guarantee the convergence of the algorithm, and we're not going to be needing too many samples to train the algorithm. So the idea, you just take any wireless network, you just basically represent it as a graph, and then do the optimization, and then give me the solution. So let's take an example. So we're going to try to learn to optimize with the graph neural network. So the idea is that I'm going to take a graph, for example, of this example, and then you put it into a graph. And then, so this is, for example, an interference channel. And what we actually going to do, instead of using DNN, where it's going to be difficult, as I explained, to make it scalable, where you're going to need a lot of training samples, here we're going to try to use the GNN, where we're going to have scalability, we're going to guarantee the convergence, and we only need a few training samples. So how am I going to do that? I'm going to give you an example where I'm going to use a K-user interference channel power control. So basically, I have multiple users, multiple base station, and then I'm going to try to do power control. So what does it mean? I'm going to try to maximize the sum rate for the system, where I'm going to have the transmit power associated with a certain base station, and we have the channel state information for a particular users. And this is a traditional problem that a lot of people have worked on. So specifically what you have a base station, you have multiple users, you know the channel state information, and you're going to actually use beamforming in order to optimize the capacity, the sum capacity. And basically what you need to do, somehow you're going to take this network and put it into a graph, and then use graph neural network like the DMP in order to give you the optimum beamforming weight. So this is a typical problem, and many people actually have worked on this. So I'm going to give you an example, and I hope you're going to appreciate this. So what we actually have done, we said, okay, let me try to look into the use of a DNN-based method. So for example, there was a paper in the proceedings of the IEEE, tried to basically solve this particular problem in 2019. This is a very important problem. And we compared it with our method based on the GNN. So what we found is that the method in the proceedings of IEEE, this is the DNN, is the following, that notice that when I increase basically, for example, the signal to noise ratio, and when I increase the number of users, when the number of users is very small, no problems. The DNN give you practically 97% in comparison to the optimal solution. The GNN also give you 98%. However, when the number of users increases, the DNN would not give you good performance. On the other hand, and as we see here, it's going to be consistent irrespective of the number of users, and it almost gives you near optimal performance. This is a very, very, very important result. And we actually have this paper in the January issue of 2021 of JSAC, which talk about how we can do that. And the emphasis is scalability and almost near optimal performance. And we've actually went ahead and this particular problem, and what we've looked at, what we have seen is that, and this is also very important, we've looking at the WMMSE. This is the theoretical, how much computation you can do. And we're looking into this GNN-based optimization. And notice this, in fact, the number of, the time it takes you to basically have the algorithm converge and give you the answer is extremely, extremely fast. We're talking about a huge reduction in terms of the speed up compared to the WMMSE, which is an extremely, extremely important thing. So let me try to now perhaps conclude very fast. I'm just going to give you something that is also, we feel, very, very important. This is the paper we just submitted. And what we're saying is that when I use the GNN in comparison to the traditional DNN, what we have found is that, for example, in this case, is that typically the GNN would require an order of n squared times smaller training sample, which is very important. You want to have a smaller training sample. So if you have an n node, so that means if we have a large network, n is going to be very small. And what we have found, for example, here we're comparing a GNN-based optimization versus a DNN-based optimization, is that the DNN would require hundreds of times more training samples than GNN. So for example, in this case, we see that with about 50 training samples, GNN can achieve almost 90% performance versus a huge number of samples if I use the DNN. So I have only a couple of slides. So I want to show you that this is just not for the sum power control, sum rate maximization. We've also used this for cell-free massive MoMo. This is also a very, very hot area where you're going to try to use massive MoMo in order to create a cellular network without any cells. So there was a paper by from Finland in this paper, they actually attempted to use deep learning based power control. So they basically, it's a minimax power control problems. And what they actually have found is that, again, it's the same problems. When you use DNN, when you actually look at the number of users, they get bigger and bigger. The performance of the DNN gets smaller and smaller. On the other hand, the GNN remains almost constant, which actually says that it achieves not only near optimal performance, but also a much, much better performance. And more importantly, it is scalable. So this is really something we feel we're pretty excited about this. And this is something really, something very, very special. So last thing I would like to talk about is there is a lot of interest right now in MoMo detection, and people talk about massive MoMo. We're talking about ultra massive MoMo. And one of the things that is going to get bigger and bigger is that when we start talking about massive MoMo, the channel is going to be huge. The channel variation is going to be a lot, especially when we're talking about now terahertz, millimeter waves, and so on. And trying to use analytical approaches to do channel estimation, channel detection is going to be almost impossible. And we have no choice but to use deep neural network. So there was quite a bit of attempt to use, for example, for the detection and channel estimation of MoMo system. And people use classic methods, for example, the MMSC, for instance. But there were some attempts, there is something pretty recent, a lot of people are working on it, is what they call a deep unrolling based method, where you try to mix mathematical models with neural networks. And this is a pretty hot area too. So we try to use the same thing, but use GNN based method. And what we can see is that certainly in comparison to the MMSC, so this is looking at the simple error probability, this is the MMSC, and this is also a neural network based method based on the unrolled method. This is the performance, but GNN actually almost give you an ideal performance. So really we were pretty excited, and we have this paper, we submitted this paper to Globecom, which talked about this result. So let me try to summarize, please. So we started with 6G, and we feel 6G is going to be important, and 6G is going to be AI empowered, not only in terms of using AI, machine learning, to basically perhaps replace decoders, transmitters, but also use AI for resource management and so on. And one of the key problems there is that how are you going to train the models and so on? And that's one of the things that we try to look at to deal with, and that's what we concluded. But in general, we are actually, as I said at the beginning, we are actually moving into a very, very exciting times. We're going to actually move to 6G, where it's going to be characterized by what I call integrated intelligence, moving from connected things to connected intelligence. And this is what 5G was all about. It was connected things. But now we're moving into a paradigm shift where we're going to try to connect intelligence, where we're going to have mobile edge intelligence, we're going to have on-device intelligence, we're going to have cloud intelligence. We're moving into a very, very, very exciting field. And more importantly, we're moving into a field where we're going to integrate sensing, communication, computing, and intelligence. And if you're kind of interested, a lot of the stuff that I've talked about at the beginning, we published it in the IEEE Communication Magazine in August 2019. As far as I know, I believe this is the first published paper which described the vision for 6G. And recently in January 2022, we have a paper on Edge AI. Edge AI is actually very popular at this stage. And we feel very happy about this paper actually since its publication. As of April, at least that's what I know, it's the most popular paper in JSAC. So we feel very happy about this particular paper. If you're interested, please have a look. But eventually, this is what 6G is going to be all about. 6G is going to basically be integrated with AI, and it's going to be a paradigm shift. We're going to actually have what I call an AI native communication, where, for example, the transmitters could be AI based, the receivers will be AI based, and we're going to have connected intelligence. This is what we call perhaps 3D networking, where we're going to have cloud intelligence, edge intelligence, connected intelligence, going all the way to the optical, where we're going to actually mix optical and wireless and terahertz communication. Another important features of 6G is that we're going to actually have include network sensing, where we're going to basically do a joint sensing and communication. And it's going to actually completely change the picture, because there I'm going to get sensing, we're going to get perhaps the use of imaging and all of that, and end up with something that is pretty exciting. And obviously there are going to be a significant amount of application, whether it's industrial IoT, autonomous driving, smart healthcare. The point I'm trying to say, 6G is going to be very exciting. It's going to require a lot of breakthroughs. There will be a lot of potential for doing a lot of research. And I'm very excited about it. And I hope I have convinced you that there is a lot of things to be done in this particular area. So with that, thank you. And I'll be more than happy to answer any question. Thank you.
Thank you, Khaled, for the wonderful lectures. So we have several written questions through the chat function. So Andrea will read them one by one. Andrea, please.
Thanks, Sherman. Can you hear me okay?
Yes.
Yes.
When GNN and DNN are compared in the power control problem, is the comparison made based on a single trained GNN that is evaluated over different number of links, or do we retrain the network for each case when we change the number of links?
So basically, that's a very important question, and this is actually one of the problems with neural networks. Is basically when you train the system is fixed. For example, you have X number of users or X number of links, and now when we move to say I'm doing 10 users, now I have 30 users. What am I going to do? Obviously, you're going to have to redo the whole thing. That's obvious. And this is actually one of the key problems. So you're going to have to change the network. But then the question is that how are you going to do that? Do you need, for instance, to can you take advantage of what you have done for the smaller network compared to the bigger one? And there are a lot of ways of how to do that. For example, in one of the papers, what we have done, the one in 2020, so we use transfer learning, for example, so that we will allow us to actually go to a bigger, say, network, but we will actually do not have to retrain the whole network. So the answer is yes, you have to, but then you can use tricks in order to minimize the retraining.
Okay, now I'm going to take a question from the audience. This question is from Bosco Liang. I'm going to allow him to talk. Bosco, go ahead. Bosco, you're muted. Bosco?
Yes. Can you hear me?
Now
yes, very well. Very well.
Oh, okay.
Thank you.
So you mentioned CNN, and what is the difference between your CNN and my common understanding of CNN for cellular neural network?
Sorry, what was the question? Sorry.
In one of the slides when you first introduced CNN, you also present you also flash up a CNN.
Yes.
And you, if I remember correctly, you kind of reference that to a convoluted neural network. And what is that? How is that CNN different from my common understanding of CNN, which is several neural network?
I think I just wanted to simplify things, and I wanted to simply use, when I introduced the CNN, it was in the context of image processing. And the reason I wanted to do that, I wanted to connect that by saying that the CNN in that context tried to take advantage of the structure, which is somehow the convolution between the pixels. That's the only reason I did that. And I wanted to relate that to the GNN, where we're saying that instead of the pixels, now in the GNN, we're trying to look into the nodes. So that's the only reason I introduced that. I just wanted to make it simple so that I can relate this convolution, whether it's for a pixels versus a node. That's the only reason. There is another question, if you don't mind. Also, they said, how do we know if a wireless communication related optimization can be written into a GNN format? So that's basically the key thing, is that can you basically put it into a GNN? And what we have found is that many problems, as we explained, many problems seems to be kind of naturally ready to be represented as GNN. So we've talked about, for example, device-to-device communication, interference channels, power control, the hybrid pre-coding, the cloud radio area network, so the channel estimation. So we found out that many problems that we have been working on, I'm not sure whether all the problems, but at least I've described multiple important problems that can be put in the context of a graph neural network.
Well, thank you. And kind of an unrelated problem, an unrelated question. I'm not really in this area, but since you mentioned about your GNN as an optimization problem, I wonder, how does that perform compared to some of the stochastic optimization problem algorithm that guys like Robbins, Monroe have done back in the 60s?
So obviously, if let's say we can do, so I don't know which one are you, so let's say, let me put it in a simple way, assuming we can do an optimization based on mathematical models, convex optimization or whatever. Ideally, that would be the optimal solution if you can find a mathematical models and you can actually optimize this. That's the ideal situation. Now, for wireless network, now it's becoming extremely difficult to be able to model mathematically our system. So for example, we're talking about, let's say now, massive MoMo, they're talking about maybe having 1,000 antenna at the transmitter and 1,000 antenna at the receiver. And now for that, you're going to have a channel. So it's going to be a channel 1,000 by 1,000, and the channel is time varying and so on. And it becomes almost impossible for us to model that and perhaps come up with actual solution. And so that's why a lot of people are saying now the systems are so complicated that the best way for us to solve it is to refer to neural networks as a way to address these complex systems. So we're not saying it's going to solve all the problems. If you have no choice, you want to use mathematical models. But now a lot of people are actually resorting to AI-based method in order to do these optimization. For me, if I have a choice, of course, I will use the analytical methods, but for wireless, it may not be possible. And there is a lot of people arguing that deep neural networks or machine learning will be the right solution to deal with these problems. But as I said, then AI need to be scalable. You need to be able to converge. You need to be able to be real time, and you need to be able to basically give good solution, which is not trivial.
Yeah, good. So due to the time limitation, so we take the last question now. So Andrea, please read the question.
Sure. Thank you, Professor Letaief, for your inspiring presentation. When using GNN for wireless networks, it seems that the system should first be modeled as a graph and input to GNN. Does this mean that we first need to obtain the global information about the network before using the GNN?
It depends. It depends on the system. For example, when we talked about the But anyway, you need to have input. For example, for the case of the power control. So you're going to have multiple users, multiple base stations. So you need to have the channels, the interference channels, the channel state information. So you need to have that information when you model the network, and that becomes part of the features. And from there, you use things like the DMP in order to do the optimization. So the answer is yes. And you need to have that information, if I understood your question correctly.
Yeah. So probably one more question. Andrea, please go ahead.
Sure, let's take one from the audience from Mushali. She's been waiting to talk, so I'm going to give her that capability right now. Mushu, please unmute yourself and please go ahead.
Yeah, I heard. I'm mute. Thank you very much. So hello, Professor Letaief. So
Yes.
I have 2 questions on the Edge AI. So for the first question, so what is the source of the label data for training the federated learning? So intuitively, the user wants to access the neural network to get the inference results. However, in the federated learning, so user also need to train the model by themselves. So, I was wondering, so what type of applications or scenario the user need to get the results of the inference, but and as well as to provide the label data for training.
So make it simple. So actually, for any application you're thinking of, so now imagine you have multiple users. That could be cars, that could be IoT devices, and so on. And now think about the fact that you have a global model you're going to actually train, whatever it is, for whatever application you're talking about, autonomous driving or whatever, right? So normally what you need to do, typically the global model is going to be trained when you do the inference and testing, whatever it is going to be at the cloud. I hope you'd agree with that. But in order for you to train that, you need to have the data from the users or the clients. That could be the IoT devices, that could be the cars or whatever, right? And what happens, therefore, now you need to send your data to the cloud. And that becomes a problem because then you're going to lose your privacy. So federated learning is trying to move around this particular problem by simply saying, okay, now I have the global model. So somehow it's like you download, think about perhaps you download the model into the individual users in a way. And then the user, they use their own local data to train it. And after they train it, they will get the weights. They use the stochastic grading or whatever, and each user is going to have the weights of the model. So they will only transmit the weights, not their private data, to the cloud. And now you're going to have multiple clients transmitting the weights, and then at the cloud, you're going to do an aggregation in order to get an average. And then you actually download it back to the clients. They do another aggregation and keep going. So that's what they are doing. And the application are a lot. I mean, this is most of the application that you need to use AI, federated learning would work. And in fact, now this is probably one of the hottest topics, part of distributed learning, and a lot of people are working on this. Very, very hot.
Okay, thank you very much.
Answer your question.
Oh, sorry.
I hope I answered your question.
Okay, thank you. So
No
I
worries.
have another, I have
sure.
just one more question. So on the so this you propose the Edge aggregated federated learning and
Yes.
like the Edge as a platform to do the aggregation and to coordinate with the cloud. So I was wondering, so in which network scenario, so there is a trade-off between the communication overhead and the accuracy. So in which network scenario, the proposed Edge aggregated federated learning can demonstrate the outstanding performance, like should the model aggregation happen frequently, or some specific network scenario, the proposed Edge aggregated federated learning can be better than the cloud and the Edge-based federated learning.
So actually, you hit the nail on a very, very important question. This is actually what you have said is really a fundamental question. In communication, we are basically used to Shannon theorem, where basically we try to do a trade-off between the rate, let's say, and signal to noise ratio and so on, and you try to maximize the rate. So that was the traditional communication theory. Now with AI, I think there is a paradigm shift. We're moving to a different optimization. And this optimization is basically related to what you've said. So for example, in the context of distributed learning or federated learning, there are two things. There is basically these communication rounds, right, that you have to do back and forth. Think of them as download and upload in order to train the models, and also the accuracy, right? And obviously there is a trade-off. How many rounds do you do and how much accuracy you want to get? And there is a lot of research going on into now trying to maximize this quantity and trying to find the optimal trade-off in order to get the best performance. And a lot of work is happening in terms of, for example, using quantization in order to minimize the overhead per communication round, in terms of how much rounds you want to do. So there is a lot of research happening in this context, and it's very, very exciting research because it really gives you a new way of looking into communication system, which is the trade-off between communications as well as the trade-off and a lot of the issues related to errors happening in the channel, whether you do the right aggregation and so on and so forth. So I think you've asked a very, very important question, and a lot of people are working on this, trying to answer that specific question.
Yeah, so that's great. So on behalf of the ECE department, I would like to thank Dr. Letaief for the very inspiring presentations. Also, many thanks to everyone for being here, participating in this lecture. So we have about 90 people attended the lecture today, which is our highest yet. So
oh my God, I'm very happy.
So this concludes the lecture today. Thank you, Khaled, once again.
Well, I really want to thank everyone. I'm really very pleased. I'm very happy with the type of question I'm receiving. And this, if it indicates anything, it indicates how great you are, and this, particularly the students. And I hope one day, I love Waterloo, and I hope one day, once COVID is out of the way, that and I can leave Hong Kong because of the travel restriction, that I will be, perhaps I will do another talk hopefully soon and meet you guys and meet Sherman and everyone else in Waterloo. So thank you so much. Yeah. Stay safe, and hopefully we will meet each other very soon. Take care.
Yeah. Yeah.
Bye-bye.
Yeah. Thank you. Take care. Thank you.
Thank you so much. No worries.
Yeah.
Take care.
Thank you, everyone. Thank you so yeah. Bye for now.
Okay. Bye-bye. Thank you so
Bye.
much.
Bye.
Take care, Sherman. Take care.
Take care.
Thank you.
Thank
no
you.
Worries. No problems. My pleasure. Bye-bye.
Bye.